Pluto is a distant and mysterious dwarf planet that used to be a member of our solar system's planetary family. However, recent astrophysicists Neil deGrasse Tyson and Michio Kaku's remarkable announcements thrust Pluto into the limelight with a surprising revelation. They say this icy world is colliding with Neptune. But how does it happen, and what are the consequences of such a great event? Are we witnessing a rare astronomical phenomenon? Or is there more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune clash, a former planet that has been downgraded to a dwarf planet in part because of its unusual orbit. Pluto remains a subject of fascination and study in the astronomical community. According to the predictions of leading scientists, Pluto's orbit is nearly negative to that of Neptune. Neil deGrasse Tyson and Michio Kaku have raised red flags about a potential collision between these two planets that could be a major threat to Earth. But how is this event possible? Pluto's journey around the Sun is unlike any other planet in the solar system. It took 248 years to make a full orbit, meaning that since its discovery in 1930, not a single revolution has been completed. But the adventures don't stop here. Pluto's orbit is characterized by its highly cylindrical shape, which deviates from the orbits of the larger planets. The most unusual thing is that Pluto's orbit is 17 degrees to the plane of the ecliptic. Pluto's path is steeper than the other planets. This curvature and counterbalance add layers of complexity to its orbital pattern point. One of the interesting features of Pluto's orbit is that it is connected to Neptune's orbit. For about 20 years per orbit, Pluto comes closer to the Sun than Neptune, challenging what we expect from their positions in the solar system. This leads to a natural question. Why doesn't Pluto collide with Neptune? The answer lies in the cosmic influences of other planets. Research into Pluto's orbit began immediately after its discovery. At first, astronomers struggled to understand its unique orbit. Unlike other planets whose orbits are close to the plane of the ecliptic, Pluto's orbit is notable for its steep inclination and elliptical shape. This mystery is further deepened by the knowledge that Pluto's orbit crosses Neptune's orbit. The stability of Pluto's orbit in these problems is a testament to the complexity of space engines. The three-body problem in space is the idea of how three bodies such as Pluto, Neptune, and the Sun move relative to each other and their forces. In the case of Pluto, this problem reflects the interaction of its orbit, that of Neptune, and the influence of the Sun programs such as azimuthal library, latitude library, and VZK swing are part of this puzzle. According to astrophysicists, azimuth stacking prevents Pluto and Neptune from meeting. In this context, it means that Pluto crosses the orbit of Neptune, which is more than 90 degrees away from Neptune, so that their orbits do not cross. The latitude library refers to the vertical motion of a celestial body in its orbit. For Pluto, this means that when it approaches Neptune or another giant planet, it will be well above their orbital plane, providing another layer of protection against collisions. Another important feature is the VZK oscillation. This movement shows that even though Pluto's path may seem sudden, it can be very slow over long periods of time. These factors, as well as the influence of other planets, keep Pluto in orbit. Computer simulations in the 1980s showed that Pluto's orbit is artificial, with small variations in initial conditions leading to large variations over millions of years. Despite this, Pluto's orbit has remained stable over long periods of time. Current experiments show that Neptune, Jupiter, and Saturn all play a role in maintaining Pluto's orbit. Neptune has a unique relationship with Pluto, so for every 2 orbits Pluto takes around the Sun, Neptune completes 3 orbits. This synchronization, known as orbital resonance, helps maintain Pluto's orbit. Jupiter is also strong enough to keep Pluto on a steady course for billions of years, and Saturn's strong force increases stability. These planetary interactions maintain order and predictability in our solar system. Without these conditions, the solar system would be a very chaotic place, with celestial bodies colliding or falling out of orbit. Why are astrophysicists so excited now about the Pluto-Neptune collision? Despite the difficult forces that prevent this event, Neil deGrasse Tyson has sounded the alarm, saying that the three-body problem is a real threat. Tyson, who played a key role in reclassifying Pluto as a dwarf planet, warns that planetary interactions may not be enough to prevent collisions in the future. He warned that the crash would cause damage to the country. Renowned theoretical physicist Michio Kaku has similar concerns. Kaku thinks that studying Pluto's orbit is important to understanding the future of space exploration and space mechanics. He believes that if Pluto and Neptune collide, the event could reveal important ideas in theoretical physics, including string theory, which aims to describe the fundamental forces and elements of the universe. World. This collision can create very powerful conditions for energy and gravity, and may provide observable data to test predictions about energy and space-time. Although a Pluto-Neptune collision may destroy Pluto due to its smaller size and ice formation, Neptune's atmosphere and hurricanes will also change. The ripples from that collision will be profound and may contribute to the understanding of the fundamental laws of the universe. Although the direct impact on Earth is limited due to the great distance, the scientific results are quite impressive. In addition, the theory of orbital chaos and the three-body problem have been proposed. Beyond just Pluto and Neptune, the study of planetary orbits also sheds light on broader cosmic phenomena, such as the gravitational dynamics of exoplanets and distant star systems. The knowledge gained from studying our own solar system's mechanics can be applied to understanding the behavior of other celestial bodies in faraway regions of the galaxy. As we venture deeper into space exploration and technological advancements in astronomy, the implications of these findings may help guide future missions, prevent potential threats, and unlock mysteries that still elude us today. The interplay between gravitational forces in the solar system also raises questions about the potential for other catastrophic events beyond a Pluto-Neptune collision. Rogue planets, gravitational shifts caused by merging galaxies, or the late heavy bombardment theory all point to the inherent volatility of space. These phenomena show how stable systems like ours can undergo dramatic changes under the right conditions. For Earth, understanding these dynamics not only helps predict global events, but also helps prepare for the consequences of changes in our galactic environment. Additionally, the study of Pluto's orbit and its interaction with Neptune serves as a reminder of the importance of continued observation and exploration. As our telescopes and technology advance, we discover new information about distant celestial bodies and gain new insights into their behavior. Tyson and Kaku's call for vigilance reflects the idea that our understanding of space is still evolving. As we unlock the mysteries of the universe, each discovery brings us closer to protecting our planet and advancing our understanding of a wider and more interconnected world. So, while Pluto's orbit is currently stable, the complexity of its celestial mechanics reminds us of the unpredictability of the universe. Tyson and Kaku's warnings about a possible collision between Pluto and Neptune serve as a reminder that our understanding of space is still evolving. Their knowledge prompts continued investigation and study, which may one day help us predict and perhaps prevent future catastrophic events. Understanding these interactions will help us better understand the dynamic nature of the solar system and our place in the universe.